Hey everyone, this is the sixth lecture of our EDUC 7610, the regression course. We're going to talk about inference and assumptions. This is a really important topic in order to really use regression in practice. It's going to really enforce what we've already done a little bit and add to it. And so far in our recordings, we've talked about significance and talked about p-values, but I haven't really addressed it really head on. And so today that's exactly what we're going to do. Just to give you an idea, generally what we end up doing, the whole picture, it looks kind of like this, where we have a population. We're interested in some aspect of that population, maybe how they respond to something, what they naturally do, things like that. We're going to be taking a sample, which is just a subset of the population. We might run an experiment with that sample and we're going to get data. From there, we're going to do everything in R in this class. We're going to import the data, tidy it up, make sure it's in good format. We may adjust our variables. We're going to visualize. We're always going to visualize the data, see what things look like. We're going to start modeling things. And this one, it mentions the Broom and Model R package. We're going to use mostly base R, but we'll use some Broom stuff here and there in the class. The whole idea is to take information from a sample that tells us about a population and get actionable insights from it. That's what we're going to be doing in R. When it actually comes to understanding the population from a sample, what we have to understand is what is statistical inference. And so far, we've really just used regression to describe our sample. We've talked about significance a little bit, but really haven't applied it to what does that really mean. Our goal here is to understand the population, not just a sample. So what we've done so far is called descriptive statistics. What we're going to do now is inferential statistics. And this relies on this idea that there's a true value out there in the population. There's some value that describes what we're looking for in the whole population. But generally, we don't have access to it unless we use a census. What we have to do is we estimate it using our sample. We try to get information about all these people using just some of the people. The problem is our sample is not going to exactly be identical to the population that we pull it from. It's not going to have the exact same characteristics and factors. So what we have to account for is what's called sampling variance or sampling error. What that means is our estimates from our sample are not going to perfectly line up with the population. We're hoping that it's close, but we can't guarantee that because we don't have the information from the whole population. So what that causes is some uncertainty in our estimates. So all these coefficients that we've talked about so far are an estimate of what the population relationship would look like. What's problematic about that is we don't know what the population looks like. So we don't know how close our sample is. This is what we're actually going to rely on statistical theory in order to guide our decisions about the uncertainty here. So just to really hit it on the head hard, the way that we use statistical inference, how we can talk about people outside of our sample, is we have to at least acknowledge, and in appropriate ways, that there's sampling variance. Our sample is not going to perfectly represent the population. So before we even can start to make inferences about the population, we need to make some assumptions about our data, about the model. These assumptions actually help us be able to make the inferences that we want to. Otherwise, if these assumptions really don't hold, if they don't line up with our data at all, then the statistical theory we're relying on to make the inferences won't really work. The first assumption is linearity. It's that the relationship between the outcome and the predictors, that relationship is approximately linear. There's ways to relax this. We're going to talk about polynomial regression and others in Unit 3. But the idea is that a line needs to represent the relationship well enough. Second one is homoscedasticity. This is where the conditional distributions of y have equal variances. Now, if that didn't make a ton of sense, that's okay. I'm going to try to really hit this one clearly for you in just a moment. But the idea is that the dots around the best fitting line have roughly the same variance across the whole line. And I'll show what I mean by that in just a moment. The third one is conditional distribution of y is normally distributed. There's a really simple way to check this using what's called the QQ plot. I'm going to show you a number of those. The idea is that y itself doesn't have to be normally distributed. Your outcome doesn't have to be normally distributed in a regression. It helps, but it doesn't have to be. What we're going to check is actually the conditional distribution of y is normally distributed. And then the last one is independent sampling. Each member of our sample needs to be independent of the other members. That means we don't want to collect data on spouses where we have both spouse and we're treating them as independent because they're going to influence each other's data in some way or another. Kids within classes is another way that we often violate this, where the kids are going to be influencing each other and they both have a shared teacher or shared environment, which could influence their values in the data. So first, linearity. There's a lot of ways that we can adjust for this one. So this one is not a serious problem, but we need to know when it is a problem so we can adjust for it. The first one is showing a linear relationship. A line really fits it well. A nonlinear, where it's more of a square root, where you kind of have this, it goes up and then kind of trails off a little bit. That is really common for these kind of situations. And then when you have this other one, which is a squared version, it's a quadratic relationship. It's where it curves up. It just keeps going up. All of these are fairly common in practice. Sometimes they're not super strong, and so it's not really necessary for us to adjust for it. But sometimes it's really important and even part of the research question, and so we'll want to look at non-linearity as well. Homoscedasticity is where the variability around the line is roughly equal across the whole line. So on this side where it's heteroscedastic, that's showing the variance is really small on one side and gets really big on the other. It fans out. Where the homoscedastic one, the variance is roughly the same across the whole thing. You'll also see homoscedastic where it kind of looks like a football shape a little bit. That's okay, because the really extreme points, there's going to be less of those, and so it may look like the variance isn't as big for those. That's all right. But there's going to be some very strong patterns that I'm going to show that are problematic. One of the most common is this fanning out one. The conditional distribution of y is saying at each point of x, there's an assumed normal distribution around the line. What's nice about this is that the central limit theorem helps us here. It is this theorem that as your sample gets big, the reliance on the normal distribution becomes less and less and less. Samples above 30 don't rely on this assumption as much. Still, though, you should check it. If it's wildly wrong, there's ways that we can adjust for it. And then independent sampling. Each member of our sample needs to be independent of the others. There's no influence from one member to another. That's really important. I've already named a few situations where this could be violated. It's great practice to think about your field and think of some situations where this might be violated so that you can keep an eye out for it. When you do violate it, often what we're going to use is multi-level modeling techniques. There's a class here at USU that talks about this. It's really related to regression. It's going to build on what we are talking about in this class. It just extends it to be able to handle these situations. All right, so what about violations of these assumptions? So linearity, if this is violated, we can try different specifications. We can try a square root of a predictor, or a square root of the outcome, a log transformation. Otherwise, if you don't catch this, and there really is nonlinear relationships happening like a curve like this, then violating this one is disastrous to the model. Your coefficients are going to be totally wrong. For example, if the relationship is really curvy like this, then there might be a really strong relationship that's curvy, but the coefficient will be totally flat, which is totally wrong here. So violating this one when it's strong is really problematic. The second one, homoscedasticity, it can mess with your standard errors. So the first one can mess with your coefficients themselves. Number two, homoscedasticity will mess with your standard errors, which will make it so your significance, your p-values, all that stuff is wrong. So it is problematic as well. There's some pretty straightforward ways around it. We can use sandwich estimators. We can use robust standard errors. We can use what are called resampling techniques. We'll talk about that later. So there's ways around that as well. The third is a conditional distribution of y. It's often not too bad in larger samples. Sometimes we can adjust this with a transformation like what we were talking about with linearity. But if your sample's big enough, it's usually not a huge issue. And then the fourth one, independent sampling, it can sometimes really mess up your results, especially if there's like the Simpsons paradox thing going on that we talked about before. We're going to use multi-level modeling to fix this. So one of my major points here is that when the violations happen, it's not going to destroy your data. It's not going to destroy your model. But you need to know about it so that you can adjust for them. If you don't adjust for them, then it can destroy your model. But just having these and knowing about them, we can always adjust. That's one thing that's great about regression, is it gives us that flexibility to do that. But if we don't ever check our assumptions, we don't know that we're violating any of these, then we're going to have problems. It always comes back to the residuals, right? So the assumptions and residuals always go together. All of the assumptions actually can be framed in terms of the residuals themselves. When we're talking about each of the assumptions, we're going to be looking at, are the residuals normal? Are they homoscedastic? Do they have a mean of 0 at all points of x? And are they uncorrelated with each other? One way that you'll see this talked about is IID. It's independently and identically distributed. It's just saying that our assumptions are holding. We're going to be using plots just like this to assess our model's fit. Each of these panels is going to tell us something slightly different about our model and will help us understand what assumptions we may have problems with and what things we might want to adjust for. We'll go through these in just a moment, just so you know. So let's try an example. So let's say we have a child language researcher wants to determine whether the length of a child's story, the word count, how many words are in there, is a significant predictor of its narrative quality. They run a simple regression and get the following results. So they run this model. If we look at the word count estimate, we get 0.053. We can look over at the p-value, it's significant. So for every 1 word increase, we expect the narrative quality to go up 0.053 units. However, before we make any really strong conclusions about this, we need to check our assumptions. If our assumptions are wrong, then that estimate doesn't really tell us anything, and the p-value doesn't tell us anything. When we're checking assumptions in R, what's really nice is we just have really two functions to run. So we run our model, that's up top line. With the LM function, we're just going to run our model, save it as model1. We could give that any name, but we're going to call it model1 here. The part MF row is just setting up our plotting landscape so that there's a 2x2 matrix. And then we're going to say plot of our model object. So plot, and then inside of the parentheses, we have our model. And this is going to produce the four plots that you just saw. The residual versus fitted, the normal QQ, the scale location, and the residual versus leverage. The residual versus fitted, that first one, it checks linearity. You want to look for a horizontal line without any distinct pattern in the dots. The normal QQ is going to check normality. We want those dots to be across the straight line. The scale location is going to check homoscedasticity. We want to look for a horizontal line with equally spread points, just like a cloud of points. And then residual versus leverage checks for influential points. We're not going to really go into this one a ton yet. It's not part of the core assumptions, but it's going to be something that we're going to need to check, and we're going to do that in the very next lecture when we talk about diagnostics. So here's the example that comes out of that model with the narrative child word count example. The first one, that residuals versus fitted, the line is roughly horizontal. You don't see any strong deviations. And there's no really strong pattern in the data. You're not seeing a curve where the dots are following each other or anything like that. It looks kind of like a cloud of points. So linearity looks good. The second one, the normal QQ, the dots fall right along the line for the most part. It's really, really good. This is saying the normality really holds. This is a solid example of that. The third one, the scale location, you see the line is roughly horizontal with roughly a cloud of points around it. You don't see as many points on the right side, and that could be a problem. But on this one, it doesn't look like there's any serious outliers over there. So the cloud of points looks pretty good here. Often you get that kind of pattern where you don't have as many up top when you have a certain type of outcome like quality, where most kids are more centered around the middle and the bottom, and then there's some kids that are really good. You're going to see that pattern sometimes. But that is an example of a good homoscedastic distribution. The cloud of points, it's really hard to find any distinct patterns where things are curving around each other or fanning out or fanning in or doing a bow tie look, which is another version that can be bad. And then the last one, the residuals versus leverage, like we mentioned, there may be some that are a little bit influential here, but we're not going to go into that yet. We'll go into that in the next lecture. So overall, I would say it seems like the model is not violating any of the assumptions. We can move forward without making any adjustments at this point based on the assumptions. All right, so a quick aside about vocab and notation. First thing that we need to understand is what an expected value is. That's the true value essentially out there. We want to arrive at the real thing that is happening out there in the world. The expected value tries to get at that idea. So if we did something 1,000 times, we just did it over and over again, we would arrive, the distribution would tell us roughly where that expected value is. What is the real value? So if we did it a bunch of times, it wouldn't be perfect, but it would start to tell us roughly where that expected value is. The whole point of understanding what an expected value is that it helps us understand what unbiased estimation means. So the E with parentheses, that's a symbol of expected value. And so what we have here with the unbiased estimation, it's an estimate that arrives at the expected value. It's an equation that will get us to the expected value every time. It doesn't mean that our sample is perfect and will line up with the population, but it means that the equation is unbiased. It will take us to the expected value the best that the sample can. So in this case, this one is measuring the mean. So you sum up all the y values and divide by however many there are, the n. And that gives us the E of y, the expected value of our outcome. That is an unbiased estimator of the mean, of the expected value. So consider this, is the following unbiased? So we want to get the expected value of y again. And this time we're going to use an equation that is 1 divided by n plus 10 with the summation of all the y's. So is that unbiased? And the answer is no. It's dividing by too much. It's always 10 too much. So no matter what our sample looks like, this will always divide by 10 too many. So when you actually, if we get a huge sample, let's say like 1 million, then it'd only be off by 10. We'd divide by 1,000,010 instead of 1,000,000. That's not going to be off by a whole lot. Hardly noticeable, but it's still biased. It's what's called, it's consistent, that as a sample gets really, really, really big, it gets closer and closer to the unbiased estimate, but it's always a little bit biased. So there's a difference between bias and consistent. Unbiased means that it arrives at it no matter the sample size. Consistent means as the sample size gets bigger, it's going to get closer and closer to the true value. What's awesome is regression is an unbiased estimator of the population value. This can be shown mathematically, and I've gone through it many times. We're not going to show it here in this class, lucky you guys, but the idea is that regression arrives at that population value. It is an unbiased estimator of what is happening in the population. That doesn't mean that our sample is perfect, but it means our estimator is the right equation. One way to think about this is what people will say is ordinary least squares regression is BLUE. That stands for Best Linear Unbiased Estimator. And each of those has a very important meaning when we're talking about the fact that it is the best linear unbiased estimator. So best means it's the most precise, it's the smallest accurate standard errors. It'll tell us the most precise information that it actually can with the data that we have. Linear it's a linear model, not too shocking there. Unbiased, it's an unbiased estimate. So it estimates a population value. And estimator, it's everything that we're doing in regression is some form of an estimate. So it's the best linear unbiased estimator. Note under my picture here, maximum likelihood regression is very, very similar in the majority of cases. And in some cases, maximum likelihood is the only one that you can use. It's very similar to OLS, ordinary least squares. And in most linear regression frameworks, it's going to give you the exact same results. But technically, OLS is what is the best linear unbiased estimator. It's BLUE. So what does all this mean then? Well, regression provides us with the best linear accurate way to understand a population using a sample. That's awesome. So regression is one of the best tools that we know out there to understand a linear relationship.